Okay, so today's the next one, lesson 19, and this is the last lesson in this section. Alright, so it's two parts. The first part's just talking about stability. Alright, so he's copied from the notes. So stability, the centre of gravity of the structure is the point through the sum of the gravitational forces, and usually that's kind of like in the middle. Therefore, the centre of gravity acts as a balance point. Alright, so if an object is unstable, it will fall out. The vertical line through its centre of gravity does not pass through its base. So here for this, if this is our base here, then at the moment that force acting from the centre of gravity, that where that weight force acts, is through the base there, so that edge will come back down. However, over on the right, so if here's the base, this time from the centre of gravity, it's acting over that, past that corner, and so what's going to happen here is that's going to fall over that way. So, as it says there, the width of the base and the height of the centre of gravity affect the stability of a structure. So if you've got something that's got a wide base like that, its centre of gravity might be there. Well, you've got to tip that over quite a long way before it's going to fall over. Whereas something like this, for example, it's not far down here for it to move before it's going to fall over. Alright, so that's stability. You don't need to know anything much more about stability other than that. But the main gist of this lesson is what we call equilibrium. Alright, so as equilibrium, the word suggests, something's in equilibrium as it's kind of all balanced. So there's two types of equilibrium. So there's rotational equilibrium, alright, so rotational equilibrium, and so in your notes, this is in your notes here. So there is one condition on this for rotational equilibrium, and that is that the net torque is equal to zero. So it doesn't mean there's no torque involved, and there's often torque involved in lots of situations, and I'll do, when we get to the example, I'll show that you there where the torques will be. So it may not look like there's a torque there, but there will be. Alright, so that's one sort, rotational equilibrium. There's the other one that's called static equilibrium. Alright, so something can be in rotational equilibrium but not static equilibrium. And so static equilibrium, it doesn't change its position. In any way at all. Alright, so in this case there's two conditions. So first of all, the net force is equal to zero. So it's not going to change its position. The other thing is that the net torque is equal to zero. So for something static equilibrium, it's not moving left, right, up or down, or rotating. Whereas the rotational equilibrium might not be rotating, but maybe moving side to side, for example. Alright, so if it's in equilibrium, or static equilibrium, then it's going to stay in one position. It's not going to move to other positions. All right, so how can we use that when we're answering questions? All right, so let's have a look at an example. All right, so here's a person stands from 1 metre from the end of a 3 metre beam. So here to here is 3 metres, and here to here is 1 metre. The mass of the beam is 40 kilograms. Calculate the reaction at support A and support B if the system is in equilibrium. Right, so there's a few things that we've got to look at first of all. So when you've got an object like a beam or something that stretches, what we do is we take its force, the weight of that object, we take from the centre. So the weight's down there, and that's, if this is 3 metres, that's 1.5 metres from either end. So exactly in the middle. The person who's standing there, of course, don't want that colour, this colour, their weight acts where they are. All right. Now, I mentioned before about rotation, and there's torque, even though you might not think there is. So say, for example, if support B, we took that out, then if we took that out, then that end would drop and it would go around like that. So there would be a torque. All right. So because this is in equilibrium and the beam's not moving down, there's got to be a force, we call it FA, down that end, and there's got to be a force, we call it FB, holding up that end. Righto. So, what things do we know? Right, we could use the translational thing. We've got the weight of the beam and the person down, and then we've got those forces up, but then we've got two things that are unknown, because we don't know force A and we don't know force B. So we're going to have to go another tack. And the other tack we do is we look at the torques, for example. And so we assign a rotational point. So what I'm going to do, first of all, I'm going to assign the rotational point here at A. And so that's the torque about A, is what we call it. All right, so I'm not going to have enough room on this page, so let's go over here. All right, 1,568 Newton, I should say. And so then when we divide by 3, the force at point B, divide that by 3, is 522.67 Newton. All right, so I did that slightly different in your notes, as it looks like in the notes I've been very lazy and I've used 10 as gravity, not 9.8, which is very poor form by myself. All right, so that's why to get slightly different results. All right, so that's the A. Now let's look at, that's the force at B. So let's have a look again at the same diagram, and we're going to have a look at and take the talk about B. All right, so here's our diagram again. We're going to talk about here this time. And so we'll follow the same process. So we've got the force at A. We've got the weight of the beam, we've got the weight of the person, and so on. So, talk about B. So again, it's the anti-clockwise is equal to the clockwise. And so what we've got to do is figure out which is turning it which way. So when we do that, anti-clockwise, the thing that's going to make it rotate anti-clockwise would be the two weight forces. So the weight of the beam is 40 times 9.8, and that's 1.5 metres from the end. The torque of the person is 50 times 9.8 times 1 metre from there. So it's 1 metre from here to here. And that equals FA times 3. When we get our calculator out, and again I've been lazy in the notes and used 10, not 9.8. Alright, we get that this stuff here is 1078 FA times 3, and then when we divide by 3, the force at A would be 359.33 Newton. And again, because I've very lazily used 10 in the notes answer is different. Alright, so there's one example, and we would use the same example, the same method for all sorts of beams and things, okay? Choose a point to rotate it by and then work out that. Now, you may or may not have picked up by choosing B and choosing A, then I don't need to worry about that torque, right? Because that torque there, because the radius of between the force at B and where the force is actually acting, the radius is 0. So the torque due to that force B in this case, because I'm choosing here at B as the rotational point, is 0. So that's what we always make a choice there. Could you choose to take your talk about here or anywhere else? Yes, you could, but it's more than likely going to make things a lot more complicated, which we don't want to do. All right, let's have a look at another example. All right, so here's an example. Figure 5 shows reinforced concrete beam. X to Z, a tourist looks out. The mass of the beam is 4,000 kilograms. Beam rests with no fixed connection on two pillars, X and Y. With no one standing on the lookout, what is the force on the beam? And then what's the maximum load that can be placed at point Z? Assume load concentrated at the end without the beam tilting. Alright, so in the first example, we've got no one standing on the lookout. So what do we have? Alright, well, what we've got is we've got the weight of the beam, and we've got this force at X, and that's what we've been asked to. So force of the beam on X. So it's also sitting here on this Y. Is there a force there or is there not? Well, how big is it? We don't know. So what we can do is we can choose to take that as our point of rotation. So if that's our point of rotation, then our clockwise torque has got to equal our anti-clockwise torque as usual. And we've just got two forces. We've got the force here that we're wanting to find out, and we've got this weight here. All right, so question is, how far is the weight? Now, if the weight is in the middle of the beam, that means it would be 6 metres from either end because it's a 12 metre beam. 8 plus 4 is 12, so that's got to be 2 metres in there. Alright, so my clockwise torque is this here. So F by 8. My anti-clockwise torque will be the weight force, 4,000 times 9.8, and times the distance it's from, which is times 2. Looks like in the notes I've been good this time, and I've used 9.8. And when we get that, we get 8F is equal to 78,400. So the force, when we divide by 8, is 9,800 Newton. Alright, so the next bit says, what's the maximum load that can be placed at Z? That's down here. So let me go to the next page and bring up the diagram again. Here we go. Street lamp has a mass of 20 kilos, is supported by a cable AB, so this is the 20 kilos up here, and a rigid rod BC. Assume the mass of both the rod and the wire are negligible. The rod, which should assume to be straight, is hinged at C and makes an angle of 30 degrees to the light pole, as shown in figure 3. Alright. Calculate the magnitude of the force in the cable AB. So we're holding this force here, which would be the tension. Now, we need to think about, because it's hinged here, we're going to take C as our point of rotation. And if it's hinged here, if A and B wasn't there, then this would swing around this way. Alright, so it would rotate about C. Alright, so let's have a look at, on the next page I'll look at that diagram again. Alright, not much good looking there because we have not given it. So I'm going to say that the length of the rod is L. And hopefully it's going to cancel out. So let's have a look and see. So the clockwise torque would be the radius, call that L, times the force, and that's the weight force, which is 196, times sine of the angle. Now that's 30 degrees in there. I wrote it in without an explanation before, but hopefully you can figure out that it would be that. And then our anti-clockwise, and that's the tension T. And so again, that's the distance L times T sine 60. So as I thought, the lengths cancel out. So the tension would be 196 sine 30 over sine 60 degrees, and that it comes out to 113 Newton. All right. So there we go. There's some equilibrium, translational and rotational, and that brings us to the end of this section. All right, so end of this section, problem set 19, and then the fourth test, and there's some revision questions. All right, there's just one video on that stuff, so have a look at that. And as always, if there's things that you're not sure of, make sure you ask. And Ben Christie, get off Minecraft.